topology of real numbers, neighborhood of a point, definition with example. So to understand neighborhood of a point, first understand this. Suppose there is a set, the boundary, and we are talking about a particular point for which the set needs to be the neighborhood. The open interval containing that point, we need to take it as small as possible. That's why epsilon is involved. P minus epsilon, P plus epsilon is an open interval that contains P. And if that open interval is contained in the set, then that set is neighborhood of point P. So a subset n of real numbers, n here is not natural number, n is any set which is a subset of real numbers. We have given it as n because of the definition of neighborhood. A subset n of real number is called neighborhood of a point P if there exists an open interval containing that particular point P. The open interval I containing point P is itself contained in the set, is itself contained in n. So set here is n, open interval here is I, which is P minus epsilon and P plus epsilon. So P belongs to I and I is contained in n. Then we say n is a neighborhood of P. So you need to remember this criteria. P belongs to open interval I, which itself is a subset of that particular set, which needs to be the neighborhood of point P. So n here is neighborhood of point P. There is an alternate definition. Like we have given I, we can give the definition I as P minus epsilon, P plus epsilon. So since an open interval I, open interval needs to contain point P, right? So the open interval that contains P should be taken in the form P minus epsilon, P plus epsilon, because it should be as small as possible for epsilon positive. So neighborhood of P can be defined in another way. Instead of I, we'll be writing the open interval P minus epsilon, P plus epsilon. A subset n of real numbers R is called a neighborhood of a point P if for epsilon positive there exists an open interval P minus epsilon, P plus epsilon, which is subset of n. Next is deleted neighborhood. See, if you have understood what is the neighborhood of a point, then from that set remove the point P. Remove the point P. The collection should not contain the point P itself. Then that collection will be called, the set will be called deleted neighborhood of that point P. So if n is a neighborhood of a point P, then the set n minus P. Remove point P from the neighborhood collection. Then the neighborhood left will be the deleted neighborhood of point P, which does not contain P, but it is a neighborhood of P. That's why deleted neighborhood of P. So it's a kind of P minus epsilon, P plus epsilon open interval removing P, the difference of P, which contains the points from P minus epsilon to P, union P to P plus epsilon. So now the examples of neighborhood. An open interval is neighborhood of each of its points. Whenever we choose any open interval, it is neighborhood of each of its points. We need to prove these results also. Let AB be an open interval. A and B are any two real numbers. AB be an open interval. X be any arbitrary chosen point in the set. We need to prove the result for X, and since X is arbitrarily chosen, the result will be true for each of its points. So X is contained in open interval AB. The set here is the set itself AB, means X belongs to AB, which itself is a subset of AB. Why? Because every set is subset of itself. And now look at this definition, X belongs to AB, subset of AB, is clearly stating the definition of neighborhood, which clearly says AB is the interval AB is a neighborhood of X. X belongs to open interval subset of that particular set, which needs to be the neighborhood. But since x was arbitrarily chosen, when the result is true for any arbitrary value, the result is true for each of its points. Since x was arbitrarily chosen inside the open interval AB, so AB is neighborhood of each of its points. Second example, a closed interval is neighborhood of each of its points except the boundary points. A closed interval is a neighborhood of each of its points except the two endpoints. We have just proved open interval is neighborhood of each of its points. We'll be using this result to prove this second result. Now we need to prove closed interval AB is neighborhood of each of its points except the boundary points A and B. To understand this, first understand this criteria through geometry. We have a closed interval, any point which is in the interior of the closed interval AB. Whenever we'll draw an open interval, that open interval will be contained in that set. But when boundary points are involved, no matter how small open interval you draw to contain that point, that open interval won't be the subset of the set. The points at the boundary are contained in an open interval which is not subset of the set. That is why boundary points are not in the neighborhood of that set. So let closed interval AB be any closed interval we are choosing, and let x be any interior point. Interior point means it belongs to the open interval AB, and for open interval we have already concluded the result that x belongs to open interval and open interval is contained in the set. That is why it's clearly stating the definition of neighborhood. Closed interval AB is neighborhood. I'm writing in the short form the word neighborhood. NBHD is neighborhood of x, but x was arbitrarily chosen, so closed interval is each of its neighborhood of each of its interior points because x was interior point. Now for boundary point, consider A first. The closed interval AB is not neighborhood of A because any open interval you choose to contain A, no matter how small open interval you choose, that will not be contained in the closed interval AB. That will go beyond the set. So that is why closed interval AB is not neighborhood of A. Similarly, it is not neighborhood of B also with the same criteria. Any open interval containing B will not be the subset of closed interval AB. So it is not neighborhood of boundary points. Next example, example third. A non-empty finite set. Whenever we choose a non-empty finite set, that is not neighborhood of any of its points. Not neighborhood of any of its points. To understand this, I am giving you an suitable example. Suppose S contains finite number of elements 1 to 5. These are natural numbers, and whenever you try to cover them in an open set, in an open interval that contains that point is contained in any open interval, the open interval won't be the subset of S because open interval always contains infinite points. How can be a infinite interval containing infinite points can be contained in a finite set? This is not possible. But we need to give the definition, we need to prove the result in a random way, in an arbitrary way. So let S be any non-empty finite set. S will be the neighborhood of a point X. If there exists an open interval containing X, that should be the subset of S. This is the definition of S being a neighborhood, but this is not feasible here. Reason being, whichever interval will contain the point X will also contain infinite points which won't be able to be contained in S. So the interval I cannot be subset of S, because S is finite, interval I is infinite. Therefore S is not neighborhood of X, and the X was arbitrarily chosen, so S is not neighborhood of any of its points. Next example, set of natural numbers. Here n I'm using is a natural number. The set n of natural number is not neighborhood of any of its points. The reason is as simple as from example 3. Natural numbers will be contained, whenever natural number will be contained in an open interval, that open interval won't be able to be the subset of n, because that contains much more points which are not natural number. So any small n belongings to n be a natural number. For epsilon positive, n minus epsilon n plus epsilon is an open interval that contains the point n. This cannot be the subset of, this open interval cannot be the subset of n, as it contains infinite points which are not natural numbers, right? So here set of natural number is not neighborhood of any of its point. Lastly, I am discussing the set of real numbers. Example number 5. The set of real numbers is neighborhood of each of its point. Whenever we choose any real number x, the open interval containing that point x will always be the subset of R. No matter what x is, whether rational, irrational, it will always be the subset of R. So R is neighborhood of each of its points. So for practice, I am doing this question. Give an example of each of the following. First of all, a set which is neighborhood of each of its points. Open interval. You can always give any open interval as an example which is a neighborhood of each of its points. The set which is neighborhood of any of its points, not neighborhood of any of its points, you need to give any example of any finite set. 1, 2, 3 I have given. A set which is neighborhood of each of its points with exception of 1 point. 1 point should not be in the neighborhood. So for this you can give semi-closed and semi-open interval as an example. One side closed and one side open, because then 2 will be the point. 2 will be the only point for which set won't be the neighborhood. And set which is a neighborhood of each of its points with exception of 2 points. For this you can give a complete closed interval, 2 to 4. Boundary points won't be included in the neighborhood. Last is a set which is neighborhood of each of its points except n points. Now you need to remove n points from the collection which are not in the neighborhood. So for this we'll be taking n points as finite. I'm choosing an open interval which will be neighborhood of each of its points union with the finite set, and that finite set won't become the neighborhood of no element will be in the neighborhood of that set. So this is neighborhood of each of its points except n points we need to exclude, and here 3 to n are the number of points in the finite set. 3 to n are n minus 2 in number. I had to include 2 more points, n plus 1, n plus 2, to make it n points in total. So 3 to n plus 2 I'll be taking, so that I can exclude n points in all.